Thank you very much. It's a great pleasure for me to be here. Thanks to organizers for this opportunity. My talk will be about the field that is called asymptotic representation theory. It studies what happens with the representations when the involved groups become large. And it turns out that like many reasonable questions in the setting can be asked in like probabilistic or analytic flavor, and this is not too dissimilar with the matrices when we study like what happens with large matrices, yes, when the size of matrix grows to infinity, and it's reasonable to ask questions about random matrices. So I will have, and actually the techniques and like in spirit, like many problems look well in spirit. Similar. So I will have two settings in my talk, two main settings. It's the settings of representations of unitary groups when the size of a group grows to infinity, and also a random matrix setting which will be related to random Hermitian matrices which are unitarily invariant. And also I will say just a couple of words about like symplectic and orthogonal groups. And also I will have two main limit regimes. So what do I mean by this? As I said, we study what happens in the limit as the size grows to infinity, but then also like the spectra of matrix or the representations can grow, and it turns out it can grow in various ways. And it's there are, I would say, two well-known limit regimes. And one of them, so how exactly these representations or these spectra grow. And one of them is more related to some probabilistic questions, and I will start with this regime. So it's related on the level of random matrices, it's related to free probability, and on the level of representations, it's related to random tilings, and also like there is connection with free probability, and the tensor products of representations appear. So this I would say like more probabilistic somehow regime of growth. But there is also another one, also I would say well known, so it stems from a very different motivation. So motivation in the second one comes from the following idea. So instead of considering what happens like with a matrix, like for finite n, with n going to infinity, we can try to analyze infinite matrix and some objects that live like on the infinite level immediately. And for the unitary groups, one can analyze the infinite dimensional unitary group and some like representations, or like I would say in more detail what exactly, related to infinite dimensional unitary group. And it turns out that these infinite dimensional objects, they can be also somehow understood in terms of approximation from a finite level. So the main motivation is these infinite dimensional objects, but they can be approximated by finite dimensional one. So we again have some growth of representations or matrices, but this is a different regime of growth. So there are two, two different situations. And the first goal of my talk is to discuss, so I have two settings and two growth regimes, so I will discuss these 2 times 2 equals 4 scenarios, and just like present briefly some results from these scenarios. And the second goal is to actually like emphasize certain similarities between these regimes, certain, I would say, suspicious similarities. And to add one more similarity, I will present interpolation between these two regimes. So actually like continuous interpolation between these two regimes, and I will call this like somehow intermediate regime. But most of the talk will be about these somehow two settings and two limit regimes. So I will start with random matrices and how like free probability appears in random matrices. Assume that we have n times n Hermitian matrix, and let us fix eigenvalues of this matrix. So for these eigenvalues, we can put weight 1 over n into each of these eigenvalues as like a delta measure on the real line. So this is called empirical measure of a matrix. And then we can ask the following questions. Assume that we have two Hermitian matrices. We know their eigenvalues. What can we say about the eigenvalues of their sum? So like this is actually like this was like a well-known conjecture. For many years, about 20 years ago, it was solved for finite n. But like our interest will be more probabilistic. So the questions can be phrased: what happens typically with the sum of two Hermitian matrices with known spectra? So what does this mean? What does this mean typically? Okay, so we need to have some probability measures, and in order to get like some actually simplifications, we also need to let n go to infinity. So the setting is the following one. So we, for each n, we fix two sets of real numbers from a1 to an and b1 to bn. And then we consider random Hermitian matrices with these fixed eigenvalues. So there are many Hermitian matrices for a fixed set of for fixed n tuple of eigenvalue, and we need somehow to take them uniformly. So like in more details, we take a Haar distribution and rotate like a Haar measure on the unitary group and rotate by this random matrix, diagonal matrix a1, a2, an. So we obtain two random Hermitian matrices, A of n and B of n, and we assume that these two rotations, they are independent of each other, so these two matrices are independent, and they have fixed eigenvalues. And we ask what happens with empirical distribution of the sum of these two random matrices. So this is a theorem of Voiculescu from about 30 years ago. So for this, in order to formulate it, we need to assume what happens with our input. So our input are two sets of eigenvalues, a1, an, b1, and bn. And as an assumption, we assume that the empirical measures, so with these measures where we put weight 1 over n, so these measures weakly converge to some probability measures m1 and m2. So this is just like arbitrary probability measure on the real line, basically. And then the theorem is that if we sum two random Hermitian matrices, we obtain certain random empirical measures. So now the spectra is not deterministic, it's random. And but this random deterministic measure satisfies law of large numbers, that this somehow it converges to a deterministic measure. It's like, one can say in what sense, so it's like a weak convergence in probability. So we take, for example, moment, and this moment of a random measure is a random variable, and this random variable converges to converges in probability to the same moment of the limiting measure. And we also obtain a certain operation on measures. So for every two measures, we obtain this concentration of measure around the limit, and this measure is somehow like a non-trivial measure. It's obtained in a non-trivial way from M1 and M2, and this operation is called free convolution, and this theorem is in the heart of all applications of free probability to probably many applications of free probability to random matrices. So what I want to emphasize that this theorem of Voiculescu, there are many proofs. I want to tell very briefly about one of them. So it's related to Harris-Chandra-Isaacson-Joubert integral. So what is written here? It's a certain integration over Haar measure on the unitary group. So this is a unitary group, and we take a diagonal matrix with eigenvalues a1, a2, an. And we consider integral, well, it's quite long, but this is like an important object. So we take diagonal matrix b1, bn, we conjugate it, then we multiply by another diagonal matrix, take a trace, then take exponent, and integrate over Haar measure. So this dun is a Haar measure on the unitary group. And this is a computation which is due to Harris-Chandra and Isaacson-Joubert, that this integral is equal to, well, some constant which doesn't depend on ai and bj, and then this is like quite compact expression. So it's compact but not simple, and has the main reason why it's very explicit but not simple, because if we plug like a1 equals a2, we have a 0 in the denominator. So because we have a determinant here, we also have a 0 in numerator, and this is actually well defined, but like somehow to resolve this singularity, it's somehow that's like where complexity appears when we are trying to resolve such singularities in this expression. Now, like I want to mention the result of Guérin-Maïda. This work was actually mentioned in the previous talk as well. So that certain asymptotics of this Harish-Chandra integral is somehow like it's possible to extract Voiculescu's theorem from a certain asymptotics of Harish-Chandra integral. So this asymptotics has a quite peculiar form, which I want to say in detail. So what we do with this expression? So we have a function of 2n variables, and it is symmetric in like if we swap these 2n tuples, we get the same function. But despite of this symmetry, we do two very different things with these two expressions, with these two n tuples of integers. So with one n tuple of with two n tuples of reals, with one n tuple L lambda 1 lambda n, so we keep them all somehow non-trivial, and we do something which is related to this empirical measure operation to this n tuple of reals. Namely, we put weight 1 over n into each of the points lambda I. We also scale by lambda I by n, and we consider this measure on the real line, and we assume that this measure converges weakly to some probabilistic measure on the real line. So with the other n tuple of variables, we do something very different. Namely, we put almost all variables to be equal to 0. And we just keep finitely many, so finitely means that it doesn't depend on n. So finitely many of them are non-trivial. And the question is how the logarithm of this function behave as n goes to infinity. And the result of Guérin-Maïda is that these two statements are essentially equivalent. So I need to explain in what sense I have a convergence. So this arrow, so this convergence as n goes to infinity, and here this is a function of just finitely many variables, are variables, and there are many ways how to make sense of this formula. So the weakest one is to say that we consider just a point 0, 0, 0. Oh, so that's a misprint. So that should be 0, 0, 0, 0 in R-dimensional space, and we consider all Taylor coefficients at this point, and these Taylor coefficients as n goes to infinity converge to Taylor coefficients of this function. So somehow this is like infinitesimal convergence of just Taylor coefficients. And one can consider several stronger senses that, for example, one can consider convergence in some small neighborhood of this point. This will also hold. So there are just like some minor technical differences, but essentially, so we know like how to think about this, that this function of R variables converge to sum of functions of one variable. So that's the main point in some like sense in the neighborhood of point 0, 0, 0, 0. And from this theorem, one can like Guérin-Maïda showed that one can deduce Voiculescu's theorem, and in particular, if we take a derivative of this function, we get an R transform of measure mu. So this measure mu, of course, it's related to this function which appears here, and its derivative is just like R transform. So we see, so this is like one indication of this connection. So R transform, which is like analog of logarithm of characteristic function from classical probability in free probability, is just appears from this analytic statement about asymptotics of Harish-Chandra integral. So this was like my first scenario, random matrices and like probabilistic growth in it. So now what corresponds to this level for representations? So first let me recall a couple of facts about representations of the unitary group. So I will not need much. Okay, so we have unitary group, and I want to recall that irreducible representations of a unitary group are parameterized by n tuples of integers. And one should think about this n tuple of integers somehow as similar to spectra of random matrices, so like as n reals which are eigenvalues of a random matrix. So for every n tuple of integers, we have a certain irreducible representations of the unitary group. Actually, it's possible to basically not to work with representations itself, but to work with characters of representations. So, for example, for finite groups, we can just axiomatically define characters of representations as like certain functions on group, which satisfy like basically just positive definite function on a group, and then all properties of representations are visible on the level of characters. So that's somehow, so we just think about characters instead of representations, and we do not lose information when we are doing this. And the character of a reducible representation, which is parameterized by n tuple of integers, so the character is given by, so the character is a function from the unitary group, but it is constant on conjugacy classes, so it's determined by just by eigenvalues of the unitary matrix. And if I denote these eigenvalues as x1, xn, then it is given by a sure symmetric function, which is again defined by a certain compact, but not actually so simple formula, which is a ratio of determinant and Vandermonde determinant. So this is a character of a reducible representation. Lambda are parameters of a reducible representation, so like label or highest weight, and x1, xn are eigenvalues. So this is like, as I said, lambda 1, lambda n are analog of spectra of some matrix, but how probability appears in the representations. So it doesn't look like that these two subjects should be somehow related, right? So this is idea of Vershik and Kerov from 70s. It's like how to get interesting probabilistic measures from representation theory, and this idea is the following one. So assume that we have, well, let us say, so we have unitary group, but basically any other group will also be okay. And so for unitary group, we have reducible representations which are parameterized by, by signatures. Now assume that we have some, just like some finite dimensional representation pi, and one can decompose this pi into irreducible representations with some multiplicities. Yes, we can do this for finite group, for compact groups. Then the idea is that it's interesting and it's reasonable to consider a probability measure on the set of labels of irreducible representations. Namely, so for such a decomposition, we set the probability of lambda to be equal to like multiplicity times dimension of these representations over dimension of the whole representations. So we do not need much to define probability measure. We need to say a set of non-negative reals which are summed up to 1. And that's exactly, so if we dimension of pi is equal to the sum of dimensions here, so the sum of all lambda of these coefficients will be equal to 1. So that defines probability measure on the set of labels, in our case on the set of n tuples of integers. And like the main point of this construction is that if we consider some like reasonable representation pi, some like reasonable from a representation theoretical point of view, then we obtain interesting measures on these n tuples of integers. So I will consider a like specific representation pi in this construction, and my goal will be somehow to get a representation theoretical analog of the summation of random matrices from which I started. And in order to get this, one needs to consider a tensor product of two representation of unitary group. So if I have two irreducible representations, like they are indexed by two n tuples of integers lambda and mu, and I consider tensor product, which is a like Kronecker tensor product, which is a representation of the same group, and I decomposed it into irreducibles ones with coefficients. So these coefficients, they have a name, they are little Richardson coefficients. So for finite n, again, so this is also like quite interesting what is happening, but our motivation is like probabilistic and asymptotic, so we are trying to understand what happens with this decomposition as n goes to infinity. And for so like we can think about this as about like tensor product is a sum of matrices, and I also need an analog of empirical measure. So I will put weight 1 over n into this point, so the lambda I plus n minus y. So this is like a spectral shift. So it's in this coordinate somehow it will look better. And I scale by n. So this is also part of construction. So this is an empirical measure which I get for each n tuple integers. I put it into the real line with the use of this operation, like considering such an empirical measure. And then I want to formulate like a result which is analogous to Voiculescu's theorem in this setting. And again, I need to assume what happens with my input, with my n tuples lambda and n tuple mu. And again, my assumption is that the empirical measures in this sense, so in this sense, these empirical measures converge to some probabilistic measures on the real line. So that's the same like basically the same assumption as in Voiculescu's theorem. And now we take tensor products of such representations, decompose them into irreducibles, obtain measure like a random n tuple of integers. This random n tuples of integers goes as a random probability measure on the real line. And the question is how this random probability measure on the real line behaves. And again, as in the case of Voiculescu's theorem, one can prove that this random probability measure converges to a certain deterministic measure. So there is a law of large numbers phenomenon, and this deterministic measure is also like some non-trivial operation from input measures M1 and M2, and so we obtained this result like 6 years ago with Vadim Gorin, and this operation is not exactly free convolution, so we called it quantized free convolution. It has several close connections with free convolution, yet it's like somehow slightly different operation. So we did this, as I said, for unitary groups, and we were motivated by similar results which are obtained by Philippe Biano for symmetric groups. And also, like as in the case of random matrices, so this is like just law of large numbers, and one can also study like what are fluctuations of sum of two Hermitian matrices. So this was so we obtained like central limit theorem around this like global central limit theorem in 2016. So this is like somehow one of level, like one application like of this level of like this limit regime for representations. But there is another one which involves tilings. And now I will go to like lozenge tilings. So we have seen similar pictures yesterday. But let me recall what is happening. So there is a triangular grid, and we tile it by lozenges or rhombi. So in this triangular grid, we have somehow we glue together two neighboring triangles, and we can glue together these two neighboring triangles in three possible ways. And these three possible ways are depicted by three different colors here. So this is one way, this is another way, this is the third way. So this is just a gluing of two neighboring triangles, and there are three possible shapes how to do this. And then the question is, okay, so what we are interested. So far this like some finite picture. We have some finite domain on a triangular grid, and we tile it by such rhombi, by such lozenges. So everything should be covered, and there should be no overlaps. And it's not always possible, but when it's possible, we can ask what happens with uniform lozenge tilings, namely. We have like some amount of these tilings of a given domain. We put a uniform measure on this finite amount of tilings and ask what happens when this domain grows, or which is the similar question, what happens when the mesh of this grid goes to 0. And this question is somehow very rich, and so it's quite well understood what happens on the level of law of large numbers, but it's not, it's like actually a quite big open conjecture what happens on the level of fluctuations. But first let me emphasize that this problem is somehow very sensitive to the choice of boundary conditions, and that's actually the main technical problem in all these questions. So for example, one can consider just like trapezoids, also on this triangular grid. So this was also a trapezoid. So there are three boundaries with just like straight boundaries, and then on this boundary we just put some like some small irregularities along this boundary. And we ask what happens if the such a trapezoid with 3 like very simple boundaries and 1 like irregular boundary grow. And the picture is like if we just simulate, we will obtain something like this. So these are 3 simple boundaries, and this is like more complicated one. But it is very important for such a picture where I put this irregularity. So here I put they are green here, and they are somehow placed in 3 segments, and the form of a uniform tiling somehow fills this this arrangement very well. So if I will put like 4 segments, then I will obtain a completely different picture, which is probably not very surprising. So like it's if I just there are reasons why this is like very sensitive, but still it's somehow this is like I would say the main technical problem in analyzing such questions. So it turns out that this question about the tilings of certain domains on a triangular grid is related to representations. It's actually related to restriction of irreducible representation. So the just combinatorics match to each other, and so these pictures can also be analyzed with methods involving like Schur functions and their asymptotics. And for example, for this such trapezoid, for basically arbitrary placement of irregularities along this boundary, like law of large numbers and central limit theorem was proved like by Leo Petrov, and like by us, it's slightly by us with Vadim Gorin in a slightly greater generality. So the main result here is a central limit theorem. So law of large numbers is relatively well understood, but fluctuations question, so what are the global fluctuations of this picture around the limit shape? It's somehow complicated, and it of course depends on boundary conditions. It depends on the form of this limit shape, so on this region, how it looks like. But there is a very nice conjecture what happens in general for arbitrary domain, not just like for this like trapezoid or for some other, just like for all domains. So it is called like Kenyan-Kunikov conjecture because it was suggested by them. And like in short, people typically say that fluctuations are described by Gaussian free field, which is true, but like there is also, it's very important that this Gaussian free field appears after a certain very specific and very complicated change of variables. So this Gaussian free field lives on this liquid region. Liquid region means that we have more than one type of tile inside of this region asymptotically, and there is a very specific change of variables which involves the form of law of large numbers, in which the fluctuations will look as a Gaussian free field. And this conjecture, despite the fact that, well, it's true, so everybody believes it, so it's widely open. So far there are 2 approaches to such. Well, there are two sets of results in this direction. So one set of results, so both of them are just for some specific domains. And one set of results is that if we make like a very some assumptions which simplify the geometry of a picture, and this is like so it starts with like results by Kenyon. So for example, so there is a he proved that fluctuations do converge to a Gaussian free field if in some class of domains where in particular there is no frozen region, so all the domain, so the frozen region is the regions where we have only one tile, and somehow if we somehow simplify the geometry of the answer, then it's like in some cases this is proven that the fluctuations are Gaussian free field. And another approach is it's related to situations where we can compute something, where we can compute like correlation functions, or we can compute well, some other things. And of course, in this way we cannot prove like, so in whole generality it happens just for arbitrary domain. So we can prove just like for some classes of domains, which for which like this something, it's possible to compute something. But on the other hand, in these domains, they are somehow in a general situation, so there are no simplifying assumptions about geometry. So this picture somehow contains a lot of geometric problems. So the geometry of answer is somewhat complicated, and playing with irregularities along the top boundary, one can obtain like more and more complicated answers. So here are some collection of works where this was proved, and it contains so links to like both these approaches. And I want just to say briefly about our recent result with Vadim Gorin, that we proved convergence to Gaussian free field for a domain with a hole. So for a non-simply connected domain, so these approaches with the use of like representation theoretical information, like after some effort, one can consider even like non-simply connected regions, which again it complicates the geometry of the answer. So the Gaussian free field now lives on a non-simply connected domain, but still it's so for some relatively small class of domains with a hole, basically for domains which look like this, we were able to prove a convergence to Gaussian free field, and and we also used in an important way the work of Borodin, Gorin, and Guillenet. So this is somehow probabilistic motivation. So access to this result is a probabilistic motivation in studying these representations. So now let me, so that's a couple of words about what happens for other classical Lie groups, for symplectic and orthogonal one. So basically the short answer is basically more or less the same. We just need to take into account a certain symmetry. So for example, for tilings, we need to consider tilings with a certain symmetry, and this symmetry is slightly different in symplectic and orthogonal case. So basically we must have a tile here in symplectic case, and the orthogonal is just like it can be that the tile is not there. And for such symmetric tilings, also like by using these techniques, one also can prove similar results. But that's just a couple of words, and I want to go to like analytic part of the statements. So all these applications, both to tilings and to tensor products, are based on a statement which is quite similar to the asymptotics of Harish-Chandra integral, and this is asymptotics of a Schur function. So this is the main objects now. It looks even simpler now. So it's Schur function. So here we put ones. And so we have two somehow parameters, lambda and x. So they are now not exactly symmetric, but still these are n tuple, like two n tuples of lambdas n tuples of reals, and xi's are n tuples. Xi n tuples of reals, and lambda is an n tuple of integers. So we fixed almost all xi's to be equal to 1, and just like finitely many variables remain not fixed, so just like this is a function of r variables, and we normalize it by the value of Schur function at all ones, and then we take logarithm and like consider like 1 over n times logarithm this asymptotics, and this result is actually more or less the same as the result about Harish-Chandra integral with these scalings. So it was also obtained by Guillenet Maida. And on the other direction, somehow if one knows this, then one can deduce the asymptotics of Harish-Chandra integral through the operation which might be referred to as a semi-classical limit. So this object, normalized Schur function, it has a degeneration into Harish-Chandra integral. So it's somehow like a discrete version of Harish-Chandra integral, and if we know something about it, then we know the same thing, well, some degenerated thing about Harish-Chandra integral. So this statement can be regarded as even more important. But the spirit and of the statement is roughly the same. So we assume that the empirical measure associated to lambda i's converge to a certain, weakly converge to a certain limit, measure mu1, and we have this function of r variables converge to the sum of functions of one variable, so which is also like a very specific effect. And these two statements are equivalent. So if I will make like all necessary technical assumptions, or like what exactly like I allow as an answer on the right hand side here and there, these two statements will just be equivalent to each other. So it was first proved by Guillenet Maida, and as I said, there are like several different technical variations, like what type of convergence we consider here, what type of convergence like is allowed, like this weak convergence, whether we converge to measures with compact support or not. So there are some variations which we considered later. And this is like a very important analytic statement behind all this application. So it's one also need to do some probability if one knows this analyticity, but this is somehow like one of key parts of all these probabilistic applications. So this was a story about one limit regime in representation setting and in random matrix setting. So now let me go to another limit regime, which is related to objects from the infinite level. So this is like the third scenario. So let me start here with representations. So assume that we have infinite dimensional unitary group. So by definition, so we can embed u of n to u of n plus 1 just by like fixing n plus first vector, base vector. And this is like a natural embedding of u of n to u of n plus 1. And then we can consider like a set of such embeddings, and this is by definition the union of all such u of n's is the infinite dimensional unitary group. So in other words, this is an infinite unitary matrix such that only finite size is actually non-trivial, and outside of this finite region we have just like ones on the diagonal and zeros not on the diagonal. Now the question is about representations. So what you want to say something about representations, and it turns out that it's more accessible to talk about characters. So we can put the same axioms for characters that we can do in finite dimensional case. Namely, we call a character of u infinity a function from u of infinity to complex numbers, which is a positive definite. It's the main condition, and also it's constant on conjugacy classes. So that's the same set of conditions that we have for finite groups, but we also add one more simple condition, that it should be normalized at unity. So the value at 1 should be 1. So usually the value at unity is dimension of representations. We somehow divide by this dimension. So this is like somehow normalized characters in usual setting. And here is just definition of a character of u of infinity. And the question is, what can we say about these characters? And somehow, for example, we want to classify all characters of such infinite dimensional unitary group. And what are analogs of irreducible characters? As in finite case, this is the analog is extreme characters. So this set with these conditions is quite clearly convex, and on a finite level, the boundary points of this set are irreducible characters of representations. So here for us this will be just a definition. So extreme points of this set of normalized characters will be like somehow analogs of irreducible representations. And we will want to classify these extreme characters, so like irreducible characters of u infinity. So this is the answer is well known. So it's a theorem with like somewhat complicated history, and it's like a Dreyfus-Kulescu's theorem. And there is some explicit formula for this character, so probably don't read too much what is written like in this formula. My point here was just like that there is explicit formula for the extreme characters of a u infinity, and okay, so this formula fits half of a slide, so that's the only point. And another point is that this formula for extreme characters, so there's a function of u infinity. So this is again a function of eigenvalues u1, u2, etc. This is again the product of functions of one variable. So these characters, which looks like a function of a large unitary group u infinity, this is actually parameterized by function of one variable, and we just need to multiply the functions of one variable. So that's how extreme characters of u infinity look like. And there is also an asymptotic statement behind this theorem, behind this Dreyfus-Kulescu's theorem, and this asymptotic statement is due to like a Vershik and Kerov asymptotic approach to these questions. Namely, one needs again to consider asymptotics of sure functions. And again, this looks very similar to what we have seen just like a couple of slides ago. We consider normalized sure function. We again have just like finitely many variables which are not set to 1, and this normalized sure function, as n goes to infinity, it converges to basically to the this extreme character, so this function phi. So it is a theorem of Vershchev that all possible limits of such normalized Schur function they converge to extreme characters of U infinity. So and again there is some classification of possible like what exactly like set of limits we can obtain as a limit of such expression. Okay, let me probably skip this. So here the point is that analyzing these asymptotics, we get all extreme characters. And what happens on random matrix level? So this is the fourth scenario. And again, there is a certain asymptotics of Harish-Chandra integral, and it is related. So let me not talk much about this. So it's related to like unitary. So we consider infinite Hermitian matrices. We consider unitary invariant infinite Hermitian matrices, and then we consider ergodic, so boundary points of this set. And in order to classify them, one again can consider asymptotics of Harish-Chandra integral, and that's the theorem of Olshansky and Vershik, that if we consider, so here I put a logarithm, so instead of multiplicative form I have like just a sum of functions of one variable, so logarithm of Harish-Chandra integral, and again this quite peculiar type of asymptotics when we set almost all variables to be equal to 0 in one of n tuples. So this asymptotics of Harish-Chandra integral is actually equivalent to a convergence of this measure on the real line. So what's the difference from the previous setting is that I didn't put 1 over n here. So at each point I put a weight 1, and that's the key difference. So this is no longer a probability measure, but still such a measure can converge in the sense that all the moments starting from 1 converge to something. And these two claims are equivalent, that logarithm of Harish-Chandra function without any scaling here, so there is no 1 over n here as well, so just a function converge to something. And such a measure, not scaled by 1 over n, just like with weights 1, converge to something. So how can this happen? That means that we have weight to n, so the measure has weight n, but almost all of these like heavy points, they're around 0. So if the points are around 0, then they do not contribute to moments starting from 1. And what actually happens is that we have like probably some sequence of like lambda 1, lambda 2, which are outside of 0, some like probably countable collections, but which converge to 0, and also something happens to 0. So that's when we can have such a slightly peculiar convergence of a measure with weight n to certain non-trivial limit. And this statement allows to classify ergodic unitary invariant infinite Hermitian matrices. So now I want to emphasize that the two key analytic facts in these two like very different limit regimes look like suspiciously similar. So the only difference is 1 over n, and there is a whole bunch of similarities. So there is like the very same peculiar limit regime, the very same form of an answer. So it's just a sum of functions of one variable, which is like why the function of r variables should converge to like just like a sum of functions of one variable. And also this like so this type of behavior is also very, very similar. So despite of this like completely different motivations, I would say the key facts are closely related to each other. So this is a statement corresponding to random matrices, and this, so from this statement, let me recall that from this statement we extract free probability, and from this setting we extract like infinite matrices. And once it's written in this form, it's quite reasonable to think about approximation, about interpolation between these two known points, and it exists. So like the claim is that if I put here, for example, 1 over n to the power theta, where theta ranges from 0 to 1, then this statement will also be correct. This analytic statement will also be correct. So these two known limit regimes, they can be actually interpolated, at least on this analytic level, they can be interpolated by like the whole scale, the whole like segments, the whole collection of possible limit regimes. So this is also somehow shows that like these two the limit regimes are somewhat similar. So what happens for representations? So for representations, one has, so do not read probably the third line. So just let us concentrate on these two lines. So this is an asymptotic of normalized Schur function. And this is, it is like the claim is this asymptotics is equivalent to asymptotics of this measure. So now this measure is a signed measure. So this is measures of total weight 0. We have n atoms plus 1 and n atoms of minus 1. So this is not conventional like Akunkov-Alshansky classification, but it's possible to deduce that like what they proved is equivalent to equivalence of these two convergences. So again, some convergence of normalized Schur functions is equivalent to weak convergence of measures. So okay, now it's signed measures. And once it's rewritten in this way, so here again I will repeat. So what's the key asymptotics for these tensor products applications and for tilings application? So it has the same form basically, but with 1 over n. So Schur functions grew exponentially, and we needed to scale by 1 over n here. And here we also considered something like which looks more reasonable from random matrix point of view when we put weight 1 over n into each of eigenvalues. So these asymptotics were important for like let us say random tilings. And here I can this is subtraction of like negative part, so it converges by itself. So this is somehow a very simple operation. But in the regime, again, I want to construct an intermediate regime. It's actually important to subtract here. So this measure also by itself, it doesn't have a limit. This measure by itself doesn't have a limit. But when I subtract, them, it does have certain limit for every theta between 0 and 1. And this statement is equivalent to this like intermediate growth of a normalized Schur function. So the story is quite parallel, both in like more, I would say, researched random matrix field and these asymptotics of Schur functions, which are related to probabilistic questions. Yeah, I think it's time for me to finish.
Thanks a lot. Any questions?
For these symmetric tilings that came from the symplectic and the orthogonal group, do you have any conjecture as to what happens on the line of symmetry, like fluctuation-wise?
No, fluctuations we didn't study. So we proved law of large numbers.
Yes,
so fluctuations should be accessible by the same method, but we do not know the answer. Yeah, so it's a very reasonable question. It's just like we didn't do this.
Okay.
Yeah, and I don't know like probabilistically what happens. No, I don't know. I didn't know this. Yeah. But it's also like our technique is like about global fluctuations. So if you are interested in local fluctuations, our technique is still somehow you need determinantal kernels if you want to study local fluctuations.
So for this f theta, is it expressive? Can be expressed by the if you know like f0 and f1, can one like write down this expression for f theta in terms of those, or it would be something completely like?
So it's a little bit different. So it's possible. So I thought about this. So what is like for example for theta equals 0, there is a certain classification of limits what we can obtain. And yes, I thought what happens for like intermediate theta. So it's slightly different. So we can when for intermediate theta we already can obtain any finite measure in this limit. We can obtain any finite measure and. So we can obtain basically functions with Taylor coefficients where which are Taylor coefficients are equal to these moments of any finite measure. So it's a little bit different both from theta equals 0 or theta equals to 1, but it can be answered. So if you know these statements, then you can answer to this one as well. So you do not need new ideas.
Other questions? No? Okay, so thanks a lot, Alexey.